section, we will explore how to use the COMxL to solve the sequential quadratic programming problems. So in here, we have a problem over on the upper left. It says apply SQP method to solve the problem. Minimize the function exponential minus 4x1 plus exponential 3x2, subject to the constraint x1 squared plus x2 squared minus 1 equals 0. And the initial values of the function variable is 1 minus 1, and our multiplier is 1. So in here, there's only one constraint, so there will be only one Lagrange multiplier. So the Lagrangian function of the problem is going to be exponential minus 4x1 plus exponential 3x2 plus the lambda 1, that is for the Lagrange of this constraint, times our constraint itself. And this is our objective function, that's over here. So the SQP solver accepts input as the Lagrange function, the cells with the Lagrangian function, so the function variables, the Lagrange function itself, objective function, the number of multipliers, maximum iteration, our tolerance, and our output location. So in here, I extract my Lagrangian function and I put it in the Excel worksheet. And as we look at the Lagrangian function, that's three variables, x1, x2, and the multiplier in our lam1. So I define them in worksheet. So x1, x2, and lam1. And the initial values for x1, x2, and lambda 1 is 1 for x1, minus 1 for x2, and 1 for lambda 1. Our multiplier, our Lagrangian function in terms of x1, x2, and lambda 1 is also given as this. So I'm coming. So we have exponential minus 4x1. So we write and we refer to it, and refer to the cells containing the initial point. So exponential minus 4 times x1 plus exponential 3 times x2 plus the lambda 1 initial point times x1 squared plus x2 squared minus 1. So this is the Lagrangian function, and my objective function is also exponential minus 4 times x1 plus exponential 3 times x2. So now we start our SQP solver. It says cells with Lagrangian function variables. And the function variables must be continuous, either in the same row or on the same column, and it must follow each other. So in here we have our function variables to be these cells in the column K. To ask for my objective function, that is the cell that contains objective function, our Lagrangian function in the cell with objective function, and my number of multipliers. One thing about the SQP solver is that the multiplier must always be set under the function variables. So the function variables x1 and x2 must come before our multiplier. So I set my number of maximum iteration to, let's say, 5. I let my error convergence, and I choose this place as my output location and put it here. So I click on solve. So the SQP solver terminates on the third iteration. So we have the value of the x1 and x2 and the lambda 1 to be this value over here. And our objective function at the point of convergence is 0.176345. So this is for the first one. When our x1, x2, lambda 1 was the initial values, our objective function was given as 0.68103. That is same as when we reference it in the cells. And the error is 2.67155. And with this value, it's calculated for the second iteration. It went for the second iteration and had this values as x1, x2, and lambda 1 with objective function value of this. Now, in the COMxL, it's a built-in grad function, negative Hessian function. So say that I want to do this manually, and as we know, for the SQP, to get the next value, so let's say our xn plus 1 can be given as xn plus the negative of the Hessian of the function. So the negative of the Hessian, so Hess of the function, that is of our Lagrange function, times the grad of our Lagrange function, right? So we have it to be this, where the Sn is the initial point and the xn plus 1 is the point after the first iteration. So in the COMxL solver, in the COMxL worksheet or workbook, there's an inbuilt Hessian function that we can employ over here. So now since we have our function of three variables, the Hessian is going to be a 3 by 3 matrix. So to use the Hessian, I select 3 rows and 3 columns. And I put my Hessian. It will ask for the function itself, and that's our Lagrange function. It asks for SR, that is the cells containing the starting point. So it asks for this. And since it's an array, we fill in the result by holding Ctrl Shift and Enter. So the Hessian of the Lagrange function at the point 1 minus 1 and 1 is given as this. So this is our Hessian. And put it, so this is our Hessian. Now the grad. The grad is also going to be a column matrix in 3 rows since we have 3 variables of the Lagrange function. So grad of the function and the function variables. So I click Control Shift and I enter. So this is the gradient of the Lagrange function. Now, sorry, this must be Hessian inverse. So Hessian inverse. Yeah. So I have my Hessian, my grad. So now I have to have my Hessian inverse. So Hessian inverse. So we have the inbuilt worksheet formula or worksheet function that is called M inverse. That is for finding for the inverse of matrix. So M inverse. So of the Hessian. I Control Shift and I enter. So this is for Hessian inverse. So S inverse. So now we have the S inverse. We have our Xn. That is the X at the starting point. We have our grad of the L. So now start with the negative of the Hessian inverse times the grad L. So then put it here. So if you multiply this times this, the result is going to be a 3 by 1 matrix. That is a column matrix in 3 rows. So I select it like this, and I want negative of, so matrix multiplication, this Hessian inverse times the grad. Now I Control Shift and I enter. So we have this. So we have this as our increment, and now this plus the starting point is what will give me the next values of the function variable on the first iteration. So this, so now if I have xn plus 1, it's going to be this plus this. So you see, so as we solve it stepwise, we had our xn plus 1 value, that is our values on the second iteration to be 0.725774 for x1, that is the same as when we use the solver, minus 0.77433 for x2, and 0.351038 for the lambda 1. Are we there? So how do I check for the error convergence? So as we can see, the grad of the Lagrange function is in terms of x1, x2, and the lambda 1. But to check for the convergence tolerance of the objective function, we need to only extract the function variables. So in this case, the graph with respect to x1 and x2. So that will be our del L. So we extract them. So I'll just reference them. Right. So we find for the absolute value of this. So that is the square root of the sum of squares. So this square plus this square. So that is 2.67155. And that is the error just before the next iteration. So if I want to calculate for the value of xn plus 1 on the next iteration, I copy this and I put this in place of where the initial points are. So I copy this and I place it here. So now I want to copy only the values. So I change it to paste values. So we have our next xn plus 1 value to be 0.6666139, that is over here, and minus 0.74865 for the x2, and 0.216059 for lambda 1. And our stopping point here on the error is 0.38268. So if I want to do for the next, I copy this and I place it in here. I want to copy the values. So now our error is getting closer to what we specified, and the value of the new xn plus 1 is 0.663323. So just copy this and paste it here. We want only values. So this error is the error with respect to these values of the Lagrange function variables. So that is using COMxL to solve sequential quadratic programming problems.